We know about a variety of solar heaters on the basis of mirrors, and for example, this mirror is a reflective film on the surface of a satellite dish. Now we see the sun rays, which can create very high temperatures. These large solar power plants are other examples when mirrors help turn solar energy into steam for turbines, which produce electricity. Another example is my solar station, where these mirrors direct sun rays into this receiver. This is another one of my solar heaters. Here we see its mirrors, and its receiver is fixed to the ground, unlike this solar heater, where its receiver is fixed to mirrors. So, let's examine the features of this type of solar heaters, where its receiver is fixed to the ground, and now I will quickly show one of my experiments. These are my mirrors, which reflect sun rays to this white screen, and the rays form this spot. Now I will show the movement of this spot during a day, while my mirrors do not move. We will see photos that were taken during one day but at different times, which will be shown here, and this is the spot. So, the spot moves from morning to evening, but it always hits the middle of the white screen, and I remind you that my mirrors do not move. That is why my mirrors do not need a complicated and expensive mechanism for changing their vertical angle according to the movement of the sun across the sky. In addition, we can see that similar solar heaters have a high receiver. At the same time, these expensive solar heaters have a thin receiver, and these heaters are expensive due to the fact that it should be very precise, because its spot must be a very thin line. But our equipment does not have to be precise, and therefore it has the right to be manufactured from cheap raw materials through primitive technologies which do not require large investments. For example, these are my mirrors on the basis of cheap mylar film, and these are the materials for the manufacture of the mirrors and their frame. We can calculate that the total cost of the materials is about $5 per square meters of mirror, and it is several dozen times cheaper than these mirrors and their frame. The cost of materials for one more of my devices on the basis of mirror stainless steel sheets is less than $15 per square meter. Thus, we have seen that the spot hits the middle of the white screen during the day, but this phenomenon is only possible if the screen and mirrors are located along this east-west line. At the same time, we see that the spot moves in this direction from morning to evening. That is why our system should be a long row of a large number of these sections of the mirror and receiver, similar to this my system, where we see 9 sections which form a long row. Let's look at my next experiment, and this is the spot at noon in early October. But this is the spot position 4 days later, and we see that now it is located a little higher, and after 5 days it is even higher. Thus, the spot position is constantly rising because the height of the sun above the horizon decreases in October, while the position of my mirrors does not change. Now 1 month has already passed without changing the position of my mirrors, and we see that the spot has already risen too high, and therefore now I am changing the vertical angle of my mirrors. This is my reminder of how I change the vertical angle of mirrors of my solar station, and we see that this is a simple and quick action. So, let's look at the spot position after this situation, and we will see that the need for the next change in the angle of the mirrors will arise only after 3 months. Of course, the spot gradually rises day after day, but the speed of the rise becomes less. This is the highest position of the spot because now is the winter solstice. After the solstice, the spot will gradually lower because the height of the sun above the horizon begins to increase. This is the spot position in early February, when I have to change the vertical angle of the mirrors, as a result of which the spot moves to this position. This is the vertical angle of my mirrors in June and December, and I have to change the angle 10 times a year. However, it can be 6 or 8 times a year, if this height is greater or this distance is less. Let's turn our attention to the fact that now, near the vernal equinox, this height of the spot is noticeably small. However, the spot's height will increase in April and May, and therefore the spot will have a great height near the summer solstice. After that, the spot height decreases, and it has a minimum height near the autumnal equinox, but the height increases up to the winter solstice, and then it decreases again. Now I will try to explain this phenomena, and this is the situation of the vernal and autumnal equinoxes, when these mirrors focus the sun rays on the surface of this screen. However, this focal point does not coincide with the screen surface for this situation in summer and for this situation in winter, and therefore the spot height increases. Of course, we can fix the screen here, so that the spot height is minimal in winter. But this screen position will increase the spot height for these situations in autumn and spring, and the spot will be too big for this situation around the summer solstice. Now I remind you that the spot hits the middle of the white screen from morning to evening if this happens near the autumnal equinox, and the mirrors are located along the west-east line. But let's look at the movement of the spot near the winter solstice, and these photos were taken during one day, but at different times, which is shown here. So, we see that now the spot hits the screen noticeably worse compared to the autumnal equinox. But the situation will gradually improve in January and February, and now I show the movement of the spot near the vernal equinox during one day. We see that the spot again hits the middle of the white screen from morning to evening, but the situation will worsen day after day in April and May. Now I will show the movement of the spot near the summer solstice, but we understand that the situation will improve in July and August. Therefore the spot will again hit the middle of the screen in September. I want to clarify that the shape of my mirrors is parabola, however let's look at my next experiment. Now I temporarily installed these washers to give my mirrors the shape of a circle with a radius of 520 centimeters. We see that the difference between the parabola and the circle is not significant. This is a spot from my mirrors, which have the shape of a circle, not a parabola. We do not see a radical degradation of the focusing of solar radiation due to the conversion from a parabola to a circle. So, we are able to give this surface the shape of a circle, and this idea can radically simplify making our devices. We see that the snow does not stick to our mirrors, and this is the day after blizzard which was accompanied by a strong east wind. Let's also look at the situation after this blizzard, with the wind from the north. That blizzard also did not put snow on the surface of the mirrors, because they are located almost vertically. Nevertheless, sometimes the snow stuck to the lower segments of my mirrors, where they deviate as much as possible from the vertical position. Let's see how solar energy quickly removes this snow from the mirrors, and this is the situation after 1 hour. Another 40 minutes passed, and we see that the snow completely left the mirrors. It is obvious that the lower the ambient temperature, the worse the snow leaves mirrors. Let's turn our attention to this shadow from the receiver, and this is the shadow at the end of October. But 2 weeks later the shadow became noticeably closer to the mirrors, and here we see its edge. Now another 2 weeks have passed, and the shadow almost touches the bottom edge of the mirrors. Obviously, day after day the shadow will rise due to the fact that the height of the sun above the horizon decreases. Now the shadow already covers the bottom edge of the mirror, and therefore its efficiency decreases slightly due to the loss of this strip. It is a shadow near the winter solstice, when it is located as high as possible. However, the shadow begins to fall after the solstice, because the height of the sun above the horizon begins to increase, and this is the shadow in early February. This picture describes my situation at the winter solstice, when this receiver is causing this shadow, which covers the bottom edge of this mirror. Obviously, I had to install my receiver here, so that the shadow would go past the mirror. Interestingly, now the mirror has a slightly different inclination, which reduces those problems due to snow sticking to mirrors. I was testing these 2 versions of the curvature of my mirrors. The focal length of the right version is 2 times smaller than the left version, and we can notice this fact if we compare these distances and the shape of these surfaces. These are the formulas of their parabola. We could notice that my video described the right version, and now let's look at the features of the left version. So, my white screen was located here, but now the distance between the screen and the mirrors is almost 2 times greater. We can notice that now the spot height significantly decreased for the case near the winter solstice, and similar effect will also be near the summer solstice. In addition, this receiver shadow does not reach the mirrors, also this is a situation near the winter solstice. Unfortunately, now the angle of the mirrors is less vertical, and therefore the probability of the snow sticking is greater, for example as it happened now. Nevertheless, we see that the snow completely left the mirrors after 1 hour. Now I am starting to show the movement of the spot from morning to evening near the winter solstice. It may turn out that increasing the distance between the mirrors and the screen reduces the time when the spot is inside the screen during a day. In addition, increasing the distance requires increasing the number of these changes in the vertical angle of our mirrors during a year.